This is a video on continuous probability distributions. So I'm going to start out today by talking about the definition of a continuous random variable. Then we're going to move on and we'll talk about the most important, or maybe not the most important, but the simplest of all distributions for continuous random variables. And that's called the uniform distribution. Then after going over the uniform distribution, we'll look at probabilities that involve the uniform distribution. And then we'll move on, and we'll say, how do we find a quartile? How do we find the first or the third quartile? Or how do we find a percentile in general if we know that a variable follows a uniform distribution? And then finally, we'll go over the mean, the standard deviation, and we'll use those to find the z-score when we know that a continuous random variable follows a uniform distribution. So today won't be that long, but it's pretty important, and it's going to set the stage for what we're going to be doing for the rest of the class, and particularly for normal distributions, which are a little more complex than the uniform distribution, but they're the important distribution for continuous random variables. So now let's talk about what a continuous distribution is. So the equation for a continuous probability distribution is called a probability density function. Remember that a variable is a continuous random variable. That means it could come up and be any number within an interval. And that interval could either be like between 0 and 1, or it could even be between negative infinity and infinity. So we're not talking about discrete random variables anymore, where we only had maybe 10 different possibilities, or only the whole numbers as possibilities. No, now the possibilities are all numbers on the number line, or all numbers between two fixed points. There's going to be an infinite, uncountable number of answers that you can get when you are selecting your random variable. And the function now, we can't draw a table anymore because there's just an infinite number to draw in the table. We can't even use dot, dot, dot notation. But what we can do is we can sketch a graph, or we can show an equation that will represent that probability density function. And it'll look like some picture like this, where you have a curve above the x-axis. I'm going to define the cumulative distribution function as the area to the left of some value. So here's a value b. The cumulative distribution function is the area to the left of b above the x-axis and below the curve. On the other hand, we're going to say the probability that x is between a and b, so it's greater than a and less than b, will be the area above some value a, that might be here at a, and below some value b, under the curve and above the x-axis. By the way, if you wanted the probability that x was greater than b, that would be this white area, or the area to the right of the value b, below the curve and above the x-axis. So now let's look at some properties of continuous distributions. The first property is that the probability density function can never be negative. It can be 0 at some values, but it can never be negative. It just doesn't make any sense when we're talking about probabilities to talk about negative numbers. Probabilities being negative just never happen, so we're not even going to go there. So the probability density function can be 0 or positive. The total area bounded by the probability density function and the x-axis is always equal to 1. we're going to be using that over and over and over again. Okay, and that makes sense because that says the probability of something happening is 100%. So if you throw a dart at a number line, then the probability that you're going to hit somewhere between negative infinity and infinity is 1. That makes sense because that's everything. But there's one thing that you may feel that's true that's not, and that is the probability density function can reach values greater than 1. That feels wrong because we learned for discrete probabilities that you can never have values greater than 1 for discrete probabilities. But for continuous distributions, you can. And that's because we're talking about area under a curve. For example, if we're only between 0 and a half, you're going to have to get bigger than 1, because if you stay under 1, then the area between 0 and a half would be a half. But the area for all values must be equal to 1, and you can't be restricted to a half, so it's going to have to average at 2, for example. So don't be surprised if probability density functions get higher than 1. So now I have an example for you. The number of seconds after the exact minute that classes end follows a uniform distribution. The graph below shows this distribution curve. Find h. Okay, so a uniform distribution means that it's the same for all values. So when a function is the same number for all values of x, then the graph of that function is a horizontal line. And if we're talking about the seconds after the class ends, that seconds hand can only be between 0 and 60, because when you hit 60, you start over again at 1 second, for example, or a half a second. So this uniform distribution is between 0 and 60. We want to find out what the height is. So we're going to use the big formula that talks about the area under the entire curve must be equal to 1. So we could say that the area is 1, and because we have a uniform distribution, we're talking about a rectangle here. Areas are hard in general to compute, but areas of a rectangle are very easy to compute. So if you remember from your basic geometry, the area of a rectangle is the base times the height. So the base times the height is 1. And the base of this rectangle we could compute as 60, or 60 minus 0 if you want. That's the base of this rectangle. The height of this rectangle is h, so we could say 60 times h equals 1. And now we get to do some very basic algebra. Don't you wish this is the hardest problem you would ever get in algebra, but that wasn't true in your algebra classes? But for us, we don't have to do some real difficult algebra. Just 60 times h is 1. And to solve that, we just divide both sides by 60. And what we get is h equals 1 over 60. And there's the height of the rectangle. So now let's use that to answer some questions. So let's find the probability that a randomly selected class will end with seconds hand between 10 and 30 seconds. So I'm going to start by drawing this picture. So again, we have this rectangle between 0 and 60. But we also have another rectangle between 10 and 30. Because remember, the probability that x is between 10 and 30 is the area under the curve, or in this case, the area under the straight line segment between 10 and 30 above the x-axis. And that area is the probability that x is between 10 and 30, which is a rectangle. And areas of rectangles are, again, the base times the height. the base of this rectangle is 30 minus 10. And the height of the rectangle, we've already found, was 1 over 60. And now we just do the arithmetic. 30 minus 10 times 1 over 60. 30 minus 10 is 20. 20 divided by 60 is the same as 2 over 6, which is 1/3. So we could say that the probability that the seconds hand will be between 10 and 30 is equal to 1/3. So let's look at another example. Let's find the first quartile for the same question. And by the way, this notation, x tilde u 0, 60, x as the random variable x, the tilde means has the distribution. U means uniform. 0 means with the low value or the lower bound at 0. And 60, in this case, means the upper bound is 60. And the question is, find the first quartile. So the first quartile means that we're going to pick this value right here, which is we call Q1, and we know that the area to the left of Q1 must be 25%, because the first quartile is the 25th percentile. So the area is 0.25. So let's set that up, recalling that the probability that x is between 0 and this first quartile, which I'll call Q1, is equal to the area. But the area, again, is 0.25. But since we have a rectangle, the area is the base times the height. The base of this rectangle will be Q1 minus 0, and the height is 1 over 60. We're talking about the same problem with the second hand. So now we just do a little algebra. Q1 minus 0 is just Q1, and I multiply left and right by 60. So I get that Q1 is 0.25 times 60, and 0.25 times 60 is 15. So Q1 is 15. Now, that should totally make sense, because a quarter of an hour is 15 minutes. A quarter of a minute is 15 seconds. So that says that the first quartile is at 15 seconds. So from 0 to 15 seconds takes up 1/4 of a minute. Okay, so let's take a look at another question. This is one of those that's going to be very difficult for you to wrap your heads around. We want to find out the probability that a randomly selected class will end with seconds hand at exactly 40 seconds. Okay, that could happen. It could happen that you're in class, the professor says the class is over, you look at the clock, and it's at exactly 40. Hopefully you agree that's a possibility. On the other hand, let's find the probability. So again, the probability is always area, and in this case, to be exactly 40 seconds means that it's greater than or equal to 40 seconds, but it's also less than or equal to 40 seconds. It can't be bigger than 40, and it can't be less than 40. So it's between 40 and 40. And that's the area under this rectangle. Well, in this case, when we draw the picture, this is a line segment. And an area of a rectangle is the base times the height. But the base is going to be 40 minus 40. That base is just 0. The height is still 1 over 60. And 40 minus 40 is 0 times 1 over 60 is still just 0. So the probability that a randomly selected class will end with second hand exactly 40 seconds is equal to 0. And that just feels wrong, but it is right. Even though it's possible for that second's hand to be at 40 when class is over, the probability is 0. That just feels weird. Here's what's going on. We're talking about a continuous random variable. When you have a continuous random variable, you have an infinite number of possibilities. And remember, before you thought about a probability being the number of ways of making you win, dividing by the total number of ways that something could happen. Well, here there's only one way that it can make you win, and that's exactly 40. But there's an infinite number of possibilities between 0 and 60 seconds. So 1 over infinity is kind of a weird thing, and you may not have thought about it before, but when you get into calculus, you realize that 1 over infinity goes to 0. So kind of a weird idea, but it really is true that the probability that the second hands will be exactly 40 is 0, even though it can happen. It turns out that it makes life easier for us. So when we're dealing with probabilities, with this little equal sign below the less than or the equal sign below a greater than, you don't have to worry about it, because putting the equal there doesn't change the probability. So it allows us to be a little bit sloppy, which is a good thing. Okay, so now let's look at another example. Let's look at kindergartners. So we're going to look at a class at which there's a rule that says when you start kindergarten, you have to be between 5 and 6 years old. That's kind of standard nowadays. Typical happens. Could be exceptions, but I'm going to just say we're going to follow the rule. So suppose that the age of a kindergarten child, when they first start school, follows a uniform distribution between 60 and 72 months old. 60 months is 5 years old. 72 months is 6 years old. Does that make some sense? And it may or may not be true. When I say suppose, it's probably not really true. But just for the purpose of our class, we're going to suppose that it's uniform, that there isn't like certain months of the year that are more likely than other months for children to be born. But we're just going to say that all months are equally likely, all days are equally likely, so that it really is a uniform distribution. Let's find the probability that a kindergarten child who is older than 65 months will be younger than 70 months. It's a weird thing to ask, but I'm doing it so that we can review a little bit about probabilities that involve given. So these are conditional probabilities. I can draw the picture. Since we have a uniform distribution, we have a horizontal line for the probability density function. We don't know the height of this rectangle. I'm going to call it h. But we do know that the base of the rectangle is between 60 and 72. So whenever we want to deal with anything with probabilities of continuous distributions that involve a uniform distribution, we need to start by finding this height. So let's do that. So again, the area under the curve total must be equal to 1. That was one of our big properties of any continuous distribution. But the area is the base times the height, because we have a uniform distribution. The base is just 72 minus 60. The height is h. We don't know it. And the area was 1. But 72 minus 60 is 12. So I'm going to divide left and right by 12, and I get h equals 1/12. So there's my height. This h is 1/12. So now I can continue on and try to figure out this probability. So remember, we wanted to find out what is the probability that a kindergarten child who is older than 65 months will be younger than 70 months. So we can write this as a conditional probability. Probability that x is less than 70, given that x is greater than 65. In a picture, and yes, it's very important to draw the picture. If you're in my class and you don't draw the picture, you will lose points. And hopefully in other classes too, because the picture is really important. So we're given that this child is over 65 months. We want to find out what is the probability that they're younger than 70 months. There's a few ways of doing this problem. The way I want to show you how to do this problem is by looking at the definition of conditional probability. And that said that if you know the probability of A given B, you take the probability of A and B and divide by the probability of B. So A and B means we're both less than 70 and greater than 65. That means we're between 65 and 70. So that's a probability that X is greater than 65 and less than 70. So the probability that X is between 65 and 70. Divided by the probability of B, or the probability that X is greater than 65. So now I compute both of these probabilities by finding the area under each of the curves. Well, for the first one, the area under the curve between 65 and 70 is the base times the height. The base will be 70 minus 65. The height will be 112. So we get 70 minus 65 times 112. For the probability that X is greater than 65, that's going to be the area of the rectangle greater than 65. That'll be 72 minus 65 times the height, which is 112. And I divide. Notice that when you divide, the numerator has a 112, and the denominator also has 112. So those actually cancel. And we just get 70 minus 65 over 72 minus 65. 70 minus 65 is 5. 72 minus 65 is 7. So my answer is 5/7. So the probability that a kindergarten child who is older than 65 months will be younger than 70 months is 5/7. And I'm done with this question. It's a little complicated, but if you remember conditional probability and you understand the probability for a uniform distribution, it's not too bad. So now let's look at one more example with this kindergarten class. Let's find the 40th percentile for this kindergarten class. So remember the 40th percentile, that means that the area or the probability to the left of the 40th percentile is 0.4. So I sketch the picture, and I say that the area to the left of some value x is 0.4. So then I go ahead and I use areas for a rectangle. So the area, again, is the base times the height. And the base here is x minus 60. The height is 112. So x minus 60 times 112 equals 0.4. Now I need a little bit of algebra. To get rid of this fraction, I multiply left and right by 12, and I get that x minus 60 is 0.4 times 12. And 0.4 times 12 is 4.8. Now I just add 60 to both sides, and I get that x is equal to 4.8 plus 60, so that x is equal to 64.8. So the 40th percentile is 64.8. And that makes some sense, that if children in kindergarten are between 60 months old, 72 months old, that the 40th percentile might be around 64.8 months. Okay, so now whenever you have a distribution or any statistics in this class, remember two really important concepts are the mean and the standard deviation. So if x is uniformly distributed, between A and B, we're going to want some formulas for the mean and the standard deviation. Well, the good news for the mean is that because when we have a uniform distribution, uniform distributions are symmetric. So the mean and the median are the same. The median is the halfway point. And the way you find a halfway point, take an average, you add the two, and divide by 2. So the mean is A plus B over 2. The standard deviation, on the other hand, has a formula that I'm not even going to try to explain where it comes from. So the standard deviation is the square root of b minus a squared divided by 12. Don't ask me where the 12 comes from unless you're really good at math, you've had some calculus, and you really understand some heavy math. I'm not going to do that in this class because it's a little bit difficult for what we're going to be talking about. But you should understand the formula. You know what a square root is. You know how to square numbers, subtract. You know how to divide by 12. So let's use this to talk about z-scores. So let's suppose that the time between when a person arrives at a bus stop and when they are seated on the bus is uniformly distributed on 230. So it makes sense. Sit down at the bus stop. Even if the bus is like there right away, you still have to get up from your chair, get onto the bus, put your money in the slot, go find your seat and sit down. That will probably take about 2 minutes. On the other hand, you could just get really unlucky and you wait and wait and wait, and finally the bus comes. 30 minutes later, you're sitting on the bus. Let's suppose the time between arrival at the airport, so when you get to the airport, and when you get seated on the plane is also uniformly distributed, but now it's 25 to 75 minutes. So if you've ever been to an airport, you have to go through check-in area. You need to get checked out to make sure you're not a terrorist. They go and look at your luggage. They look at your carry-on. You got to take your shoes off. You got to sit down. Then, of course, you always have to wait a while. So the least that it can take before you can get on the plane and sit down is 25 minutes. Okay, and let's suppose that the most you can take is 75 minutes, and that it's uniformly distributed. That's probably not exactly correct. Whenever I say suppose, just believe me, for purposes of this class, we're going to assume that's true. Same thing with the bus. We're just going to assume that's true. Okay, if it's anything other than uniform, it's more difficult. And trust me, you don't want to go there. So we're going to stay with uniform distributions for both of these. So first, let's find the mean and standard deviations for each of these. So it's not too bad. We're just going to have to follow the formulas. So remember, for a bus stop, x1 is uniformly distributed, x1 being the bus stop, uniformly distributed with low 2 and high wait time 30. And for the airplane, x2 is uniformly distributed with the low wait time is 25 and the high is 75. So let's start out with the means. So the mean is a plus b over 2, and for the bus stop, that's 2 plus 30 divided by 2, and that's 32 halves, or 16. For the airplane, that's a plus b over 2 again. That's 25 plus 75 divided by 2, or 100 divided by 2, which is 50. For the standard deviation, again, we put it into the formula, the square root of b minus a squared over 12. And that's the square root of 30 minus 2 squared divided by 12. I put it into my calculator. I highly recommend you also try putting it into your calculator so you're familiar with how to do that, so that you can actually verify that you get about 8.08. Similarly, for the airplane, the standard deviation is the square root of 75 minus 25 quantity squared divided by 12. And in the calculator, you get about 14.43. So now the second question is more interesting. Let's suppose that it took Christine 26 minutes to get seated on her bus, and it took Pedro 65 minutes to get seated on his airplane. Use z-scores to determine whose wait time was more surprisingly long. Okay, so we know that Pedro took longer than Christine, but who would be more surprised by how long it took? Because you know airplanes generally just take longer. You're not surprised if you take a long time. But 65 is pretty much longer than 26. So who should be more surprised? So we're going to use a z-score, which we've seen before in this class, to find out who should be more surprised. So if you remember, the formula for the z-score is that z is x minus mu divided by sigma. So just plug in. X for Christine was 26 minutes for her wait time. Mu was 16. Sigma was 8.08. And I put that in my calculator. That is 1.24. For Pedro, his wait time was 65 minutes. So I put in 65 minus 50, and I divide by 14.43. So Pedro's z-score was 1.04. Remember, z-scores talk about how surprised you might be, how rare it would be to be at that value. And for Christine, her z-score was 1.24 versus Pedro, which was 1.04. Christine's z-score is larger, so Christine would be more surprised. So we can conclude that Christine's time to get seated was more surprisingly long. So that's about all I have to say about continuous distributions, and in particular about the uniform distribution. Hopefully this was pretty clear to you. If not, please go over this video again, or ask me questions if you're in my class, or if you're in another instructor's class, please ask your instructor about how to work out these problems and how to understand continuous distributions and uniform distributions. So thank you again for watching this video, and ask questions, ask questions, ask questions. So I will see you at the next time when we talk about the normal distribution. The next real special, not quite as easy. We're going to need calculators in a big way to come up with probabilities. So take care. Have a great day. Have a great morning. Have a great night. Whenever you're watching this, just have a great time. See you later.